Right, so with this situation here, Q is struck, okay, with a speed 6, and it'll keep going. It'll keep going in that direction, okay, because this string is not taut, isn't it? It's slack. Distance between P and Q is 3, but as it keeps going in this direction, the string is going to get less slack, and it's going to get to a situation where you've got P here, and then the string is actually hitting its full length, right, of 5 meters. Right, eventually, but Q is just travelled, it keeps going in this direction until we get 5 meters, till that string gets to its max. Okay, so it's still going, right? Still going to have a speed of 6 in that direction, still going in that direction, and then of course it becomes taut on 5 meters. All right. Now what doesn't change here, it's important to see, is this horizontal distance here, so to speak. Well, it's still going to be 3, isn't it? Because if you think about it, Q started down here, didn't it? And then it sort of went in that direction. Okay. Well, this stays as 3, doesn't it? And what's good then is you've got a right angle triangle, Pythagoras. That's 3, that's 5. It's got to be 4, isn't it? Okay, using Pythagoras. Now, when it comes to part A, right, or these questions here, it says calculate the speed of P and Q immediately after the string becomes taut and so on. You need to be able to resolve along the string, direction of the string. Now, this 6 here, this is sort of not really going in that direction. So we need to sort of get components along that string. Okay, so that's important. We need the component along the string, yeah, and perpendicular to the string. Okay, that's important as well because we resolve perpendicular to the string. So along the string, and we've got this 6 here going in this direction, so maybe we can call this angle theta here. Okay, so we can sort of resolve, right? Now if you think about it, this is going to be 6 cos theta, isn't it? And this is going to be 6 sine theta perpendicular to it. And what's even better is, because that's theta there, you've got theta here. Okay, and you can work out what it is. You can work out then, because theta is opposite angles here, you can work out what theta is in terms of cos and sine. So cos theta, okay, here, adjacent over hypotenuse, and sine theta, opposite over hypotenuse. Okay, so we've got those components resolved there. Okay, so ultimately we know this is going to equal 6 cos theta is going to be equal to 6 times this, so that'll be 24 over 5, and 6 sine theta will be 6 times this, which will be 18 over 5. Okay, so then what we need to do is we need to then look at the components of the velocities before. Okay, in this situation we've got here. Okay, so maybe another diagram will help. Okay, so this is a bit clearer for us. So the before situation, just as the string, or just before the string is becoming taut. So this is 5 meters. Okay, but just before, okay, what we've got in this case here, a horizontal component, a component that's going along the string, which is 24 over 5. Okay, which you maybe write as a decimal, 4.8. Perpendicular to the string then, 18 over 5, which is 3.6. Okay, this is before. Now this obviously hasn't moved. After, situation after, okay, well P now starts to move, and remember P will move along the direction of the string. Okay, it will move along the direction of the string. It won't be moving perpendicular to it because it just gets pulled by that string. So it's going this way. So call that U. This here then, well of course these will have new velocities. Okay, Q will no longer be going at 4.8 and 3.6 in those directions because there's a jerk in the string, isn't there? You know, and it sort of gets pulled back and so on, right? Its speed's going to be affected both horizontally. But what's good is, you know, that's got to be U. That's got to be the same as this. Okay, it's got to be the same because the string is taut, right? So it's going at the same speeds, and this then we call it maybe V. Okay, so what we do now, we resolve, right? We go along the string, perpendicular to the string, right? So along the string. Okay, of course we know now. We're not given the impulse in this question, right? But we can say, look, momentum before equals momentum after. Okay. So we've got the momentum here of Q, right? Which is what was Q? Was that 9 kilograms, and P was 7 kilograms. That's right. So along the string, momentum before then is going to equal 9 times 4.8, and of course that's 0, isn't it? Because it's, you know, plus 7 times 0, isn't it? Equals then momentum after, well, it'll be 9 times U plus then 7 times U. Okay, so you work that out on your calculator and you get 43.2 here equals 16u. So u will be then 43.2 over 16, and that comes out to be 2.7 meters per second. Okay, so we've actually now worked out the speed of p, haven't we? So we can say, look, speed of p is 2.7 meters per second. Okay, and that's after, of course, after the impulse takes place, okay, of the strings. We need to work out v, so we'll do now perpendicular to the string, right? So we'll do perpendicular to the string. Well, momentum before equals momentum after. So momentum before perpendicular to the string. Well, we go back to this diagram. 9 times 3.6 equals momentum after then. Well, that would be 9 times v, isn't it? Okay, and there's no perpendicular component here because remember it moves along the string. 9 times v. Okay, so you work that out, and that then basically, if you do the work on the calculator, you get 3.6 meters per second. Okay, now it does want the speed of q. Okay, so afterwards, so you must remember, now I'm going to go back to this just so it's clear on the video. This v here, there, we worked out to be 3.6. U was equal to 2.7, remember? So to get the speed then, okay, you need to sort of think about those two components, 2.7 going one way, 3.6 going the other, so we use Pythagoras, don't we? So 2.7 squared plus 3.6 squared, square rooted, and we get then the speed out, which is 4.5 meters per second. Okay. It says then, find the impulsive tension, doesn't it? Impulsive tension. Well, the impulsive tension, of course, is equal to the change in momentum on one of the objects. Okay, so we can focus on the change in momentum on one of the objects, because how the momentum is changed on the object then, of course, is equal to what the impulse is in the string. So I would focus on p because that's easy. So we've got momentum after, which is 7 times u, so it'll be 7 times 2.7. Take away then momentum before, which is 7 times 0, of course, because that wasn't moving before. So you work that out, you get an answer of 18.9 Newton seconds. And then to finish off, what does it say? It says find the angle between velocity of p and velocity of q immediately after the jerk. So basically, this is going to go along this direction, p is, okay? Along this direction. So what I need is just this angle here, angle theta here. Okay, so all I need, because this is going along the string. So if I get this angle, I get the angle then that it makes towards this direction, the way p is going in. So that angle, quite simply, you just do tan theta equals 3.6 over 2.7. So you get theta out then to be 53.1 degrees.